Hello everyone, my name's Dr. Vile. Welcome to my A-Level Chemistry YouTube channel, which is all about getting you ready for your A-Level Chemistry exams. And this video is going to focus in on something called the Arrhenius equation. Now, the Arrhenius equation is found in your A2 kinetics topic, and it's used for calculating the activation energy and looking at the relationship between the rate constant and the activation energy. So how the rate constant gets affected by temperature. And in this video, we're going to focus in on how we can use the Arrhenius equation in the form of a graph to calculate the activation energy. If you find this video helpful, remember to like, subscribe, keep checking back for more content. Okay, so on the left-hand side of the screen at the moment, you've got the Arrhenius equation. I'm going to do a separate video about this where we go through how to do calculations using this one. But we need to know what all the terms mean. K is your rate constant. That's another way of saying the rate constant. A is called the pre-exponential factor, and it's, for our purposes, it's just a number. We don't really need to worry too much about what it means. It's just a number, and it normally has the same units as the rate constant. And then this little lowercase e is a mathematical term that's on your calculator. You normally get to it by pressing shift and then natural log to get it on your screen. And then EA, capital E, small a, is all one term. It means the activation energy. R is the gas constant, and T is the temperature in Kelvin. Just to be aware, in the gas constant it deals with joules, whereas the activation energy is normally quoted in kilojoules per mole. So normally to feed the activation energy into this equation, you would need to convert from kilojoules into joules. So just be aware of that, because we're going to need to do that later. Once you've got your Arrhenius equation, some very clever mathematicians have turned it into a different form where it's now in the form of y equals mx plus c. You don't need to be able to do that, but it's worth learning the two different forms of the equation. Unless you're mathematically a genius and want to be able to do it, that's absolutely fine. But it's easier just to learn, I think, the other form of the Arrhenius equation. And in this version, they've got the natural log of your rate constant is equal to minus EA over R times 1 over T plus the natural log of A. And you can see here it's in the form of y equals mx plus c, which is the equation of a straight line. So the natural log of K corresponds to the y-axis. Minus EA over R is m, which is your gradient. So we're going to plot a scatter graph and get a line of best fit to calculate the gradient. And then 1 over t goes on the x-axis. And c is the intercept, which is where it crosses the axes, and that is the natural log of a. We don't actually have to worry about that. That doesn't come into our calculations at all. What we're interested in is, therefore, if we plot a graph that has the natural log of k on the y-axis and 1 over t on the x-axis. So we measure the rate constant at different temperatures. So you do exactly the same experiment as with the iodine clock, but at different temperatures. Calculating the rate constant at each temperature, you can then plot a scatter graph of your data, which should look a little bit like this downward sloping straight line of best fit. You can then calculate the gradient of your line of best fit. And then we can use the gradient to calculate the activation energy. So that's the typical way this question goes. It wants you to work out the activation energy for a reaction. So the steps are as follows. Firstly, record rate constants for a reaction at a series of temperatures, making sure to convert your units to Kelvin so that everything's consistent. You then plot that graph we just looked at, the natural log of K on the y-axis against 1 over T on the x-axis. Calculate the gradient of the straight line plot, and then whatever your gradient is, it's going to be a negative gradient. It'll come out negative because it's downward sloping. You times it by minus R, which is the gas constant, and that'll come out positive then. And your activation energy will come out in joules per mole. So you get a negative gradient, times it by negative R. so minus 8.31, and that'll give you an activation energy in joules per mole. Now normally we then convert this into kilojoules per mole, because that's the normal units for the activation energy, because it gives us more sensible numbers. Okay, so on the screen you've got the reaction was carried out at 5 different temperatures. Notice the temperature is in Kelvin, and the rate constant was measured for each. And you have to calculate the natural log of K, the natural log of the rate constant. Be really careful here, because you've got small k's and capital K's. Don't get them muddled up. Capital K is the unit of Kelvin, and the rate constant has the symbol K, so just be aware of the subtleties there. So you first have to calculate the natural log of K, and then you have to do 1 divided by the temperature. Now that would have units, that will be Kelvin to the minus 1. So to do the natural log of K, you just get your calculator, you press the natural log button, and then 1.78 times 10 to the minus 5. And I get that to be minus 10.94. And then you do 1 divided by 633, which comes out as 0.00158. Or what might be easier for plotting this as a graph would be to write this as 1.58 times 10 to the minus 3. Okay, so on the screen now we've got all the data there, and we're ready to plot a graph. And on the next screen we're going to plot our graph. We're going to have the natural log of K, remember, on the y-axis, and 1 divided by temperature, which has units of Kelvin to the minus 1, on the x-axis. Natural log of K would have no units once you've taken the natural log, and it should look something a little bit like this. A scatter graph going downwards from left to right, where you're going to put a line of best fit through it. And then we're going to take a gradient to our line of best fit. Okay, so here's your graph. You've got the natural log of K on the y-axis, and notice you're going downwards. So you'd start with 0, then minus 2, then minus 4. To be honest, you could zoom in more than this. You could have started at minus 4. Notice that this is all wasted space on the graph paper. You know, that's unnecessary. I probably should have started my scale and zoomed in a little bit more. I'm still using more than half of the graph paper though, so I'm okay, but that is wasted space. And then on the x-axis, I've got 1 over T, which is Kelvin to the minus 1 for the units. And notice I've zoomed right in to get your line of best fit. Once you've done that, what you need to do is get yourself a ruler and draw a triangle, basically a tangent to your curve to work out the gradient. So a straight line going down, a straight line going across. And what we're calculating here is the change in y divided by the change in x. So you measure what was y at the beginning. Well, that's going to be roughly about minus 4.5 on my triangle, down to minus 10. So it's gone down by 5.5 roughly. And then it's gone across from 0.0013 to about 0.000154, let's say. So it's the change in y divided by the change in x. It should give you a negative number. When I did it in Excel, I don't know how clear this is here, so I'll make it a bit bigger. I got the gradient to be minus 22,517. Now you will not get exactly the same number as that when you do it by hand. You will get a different value. That's not a problem. What they do for the exam board for this is all the examiners will sit down and do the graph, and they will work out what their gradient is, and then they'll kind of give an acceptable range to be within. So they will do these by hand, not in Excel, and they will see the variance between their answers. And what we're going to do to finish in a few minutes is then look through what we do with this number once we've got it. Yep, so once you've got through to your gradient, remember ours was minus 22,517, you will have got it slightly different if you've done it by hand. By the way, if you are doing this at home, please don't just watch this video, get some graph paper, actually have a go at doing it. There's no point just watching it through, check you can get to similar numbers. Well, we know that gradient equals minus EA over R. And therefore minus EA equals gradient times R. So what we can do here is take the minus of the gradient, which is, well, yeah, minus 22,517, times it by the gas constant. Let's just do it that way round. So 22,517 times 8.31. And that gives me 187,116 joules per mole. And we divide that by 1,000, gives you 187 kilojoules per mole. Anyway, thank you for taking the time to watch this video. I hope you found it helpful. If you have found it helpful, then please like it, please subscribe, please keep checking back on the channel because we're constantly adding more videos. Anyway, thank you very much, and I'll see you next time.